typically larger devices, and they are volatile. In other words, you need a program when you power up. And we'll talk a bit about that. The basic structure of an FPGA is different than the CPLD. The FPGA is a lookup table type architecture. It gets a little bit fancy, but essentially you have 4 inputs into this lookup table, and then you have an output that gets registered. And then this right here, instead of going to an I/O pin, although it can go to an I/O pin, it typically goes into routing inside the device. So in that, those little devices I've been sending around, you'll see in their rows and columns, and that's essentially what this device is. It's just a bunch of these elements within that device. So you can go ahead and take the output of this 4-input lookup table, and with routing, and this part right here would be the routing, so you come out of this lookup table, you go down routing on another row, and then down a column, and then you feed into another lookup table. And then you go ahead and have more complex equations. Now every time you go through, you come out and you go into routing, that routing is you're gonna take a hit. Maybe a nanosecond, maybe half a nanosecond, depending on where this logic is located on the die physically. You have a lookup table that's located, if you can assume that this screen size is the actual die, and you've got a lookup table over here, and you need to get to the lookup table down here. The output of that lookup table has got to go down a column and all the way across the die to that side. It's going to take a lot longer to get to there than if the lookup table were right next to each other. So we've got tools to be able to lay this out and put this lookup table right next to this. The problem becomes when it gets a lot more complex, you don't have as much freedom. You know, maybe there's other logic around here that wants to get to that guy too. So, you know, at that point it gets really complex. We've got other things inside the devices, you know, like global signals that run across the device, but you're only limited on those. There's only so much routing inside this device that you can have, right? So it's a trade-off. And inside these devices, they get pretty large, as you saw with that die that's getting passed around. So for a lookup table type architecture, here it just shows you the lookup table chain. And you can go ahead and feed the output of one into the next. One of the things that we've done at Altera is we went ahead and improved on this technology. That 4-input lookup table is kind of old technology, so what we have now is an 8-input lookup table. So now we've increased the number of inputs to this lookup table to 8. We found that a lot of the designs these days are getting a lot more complex. So what we've done is we've increased the number of inputs from 4 to 8. And we can go ahead and get this lookup table that feeds these adders, which feeds these registers, and then make it kind of rearrange this lookup table. So we can go ahead and have it where, let's say I just want a 3-input lookup table, and then I can use the other 5 inputs for some other function. We can kind of do this in our devices, but it's getting a little more complex. But essentially, this is still considered the basic element of an FPGA. And our competitors, they do the same thing. They've realized that as well too, and they've got something similar to what we have.
It's a built-in adder. It's not programmable, just an edge.
That's correct. Yes. This is for DSP function. So here's the kind of layout of our device. You know, I've been talking about the basic element of the FPGA. I wanted to kind of keep it a little simple. You know, these devices do get real complex. Here it kind of shows you the complexity of it. You know, I did mention the logic elements, which is essentially a 4-input lookup table, followed by a flip-flop. But we've got a lot of other things. We've got DSP blocks. We've got dedicated multipliers inside the FPGA as well too. A bunch of 9x9s, and you can make 18x18s and 36x36. And there's advantage of having dedicated multipliers in here for DSP applications, but essentially they're in there as well too. We also have memory. There's memory blocks inside FPGAs. You know, our competitors have one size. We've got 3 different sizes. So you know, it's just a different way of doing things. But essentially, you know, you have 4K bits, or you have 512K bits of memory, and then 512 bits of memory. So there's 3 different sizes in our device, and you'll see these devices spread out throughout the device. You see these memories spread out throughout the device as well. We've got high-speed I/O channels where we can go ahead and get high-speed channels coming in. And we've got one device that will take 11.3 gigabits per second. So just one signal going 11.3 gigabits per second, and that can come directly into the FPGA. And if you think about it, that's pretty fast, right? So we can take 100 gigabits coming in and 100 gigabits going out on the same device. So with all this networking, you wonder how all this networking is going on, is because they're getting a lot of use out of these high-speed transceivers. A little different technology in terms of high-speed transceivers. You know, you can only send the data, you can't send the clock. So we got to go ahead and extract the clock from the data. But we've got devices right now that are working at our customers going in 11.3 gig. We've got also PLLs on board. These are phase lock loops. I'm sure you guys are learning this now in class, where you can go ahead and get a signal, bring it into this PLL, and then you can output different frequencies of that clock, or that signal rather, change the phase. You can do all kinds of neat things, but this is also in those devices as well too. Just so you know, you're kind of aware of it. It shows that we've got 681,000 equivalent logic elements in the device, and we've got that shipping today. It's a pretty large die. I mentioned earlier, it's got 1,932 pins of 1,932 balls, and no pins anymore. Not that large of a number. They're all balls on a die. Package rather.
Are these things like the phase lock loop, is that a special dedicated circuit, or that's implemented in the same way as a loop?
So the question was whether or not this PLL is dedicated circuitry, and it is. Everything that I've talked about, all these blocks are dedicated circuitry. In other words, if you don't use those DSP blocks for DSP applications, they get wasted. They just sit there. It's not logic elements. So by far the most part of the die is the logic elements. Everything in blue is a logic element. But we do have these dedicated blocks, the memories, the high-speed I/O channels, the PLLs. All these are dedicated blocks. If you don't use a PLL in your design, that PLL still sits there, but it's not getting used. And you know, there's trade-offs, right? It's like, okay, how much memory do you put in that device? If you put too much, it'll take up a lot of real estate where you could have used it for logic elements. So there's this constant trade-off. Okay, we're always trying to figure out how much DSP blocks do we put on there? How much memory do we put on there? Because if we put on more memory, that means we put less logic elements. Question?
The 681,000 equivalent logic elements, would I divide by 10 to figure out the number of loops?
Actually, no, that is the number of LUTs, 681,000. So to give you an idea, you know, a logic element, we've talked about this, 4-input lookup table followed by a flip-flop. We've got 681,000 of those blocks in this device. We have what we call a soft-core processor. It's a 32-bit RISC type processor. And you can stick it into our FPGAs. It takes about 2,000 logic elements. So you can potentially put 300 of these 32-bit RISC type processors in one of this device. Now, of course, it doesn't make sense to do that because of the I/O and stuff, but just to give you an idea, 300 microprocessors in our largest device.
So it's about 800 by 800?
The die size?
The loops, in other words.
Yeah, the question is
60, I guess that would be 640,000, would be 800 by 800.
The question is how many
so
rows and columns?
By 1,000.
Yeah, the question is how many rows and columns of logic elements, and yes, you do the math, just take that, 600. Let's see what else.